We'll get started with introductions. My name is Drew Lira, and I am a fourth-year undergrad student at the University of California, San Diego, studying marine biology.
My name is Wrishija Roy, and I'm a fourth-year undergraduate student at Emory University studying environmental science and chemistry.
My name is Brittany Jones, and I'm a recent graduate of Western Washington University, where I studied environmental science with a focus in oceanography and water quality.
Today we will be presenting our research on ocean acidification, specifically looking at the constraints and impacts of a solar liming intervention, both from engineering and biogeochemical perspectives. The top threats to marine life are climate change, overfishing, pollution, and habitat damage. Each of these threats impacts trophic levels of marine organisms in different ways. Global warming is a critical issue facing humanity, and there are fundamental links between global warming and ocean acidification that are often overlooked. Hundreds of years of anthropogenic carbon dioxide emissions has reduced seawater pH and increased carbon dioxide levels, and these conditions will exacerbate existential threats to marine species. We want to target this knowledge gap by considering relative sensitivities to stressors within marine biology when targeting global warming. Our goal is to enable carbon dioxide drawdown via our strategy of artificial ocean alkalinization, or ocean liming. In our research, we are assessing the scale, constraints, and impacts of artificial ocean alkalinization driven by concentrated solar energy for an effective intervention within the context of marine ecology, engineering, and politics. We aim to combat global temperature rise, restore marine ecosystems, and maintain phytoplankton health.
Phytoplankton biomass in the world's oceans amounts to about 1 to 2% of the total global plant carbon. Yet these organisms fix 40% of the total atmospheric carbon, and between 50 to 80% of the oxygen production on Earth comes from the ocean. The majority of this production is from oceanic plankton and some bacteria that can photosynthesize. Future projections of phytoplankton-induced climate mitigations are complicated by the top-down and bottom-up processes influencing phytoplankton blooms occurring along the coastlines. The RCP 8.5 carbon emission scenario has projected an increase in global sea surface temperature of about 0.05 to 0.5 degrees Celsius per decade, influencing phytoplankton growth rates and water quality parameters. Due to rising sea temperatures, stratification along the water column is projected to continue to increase, leading to a reduction of the upper mixing layer. This expanded thermal boundary prevents upwelling of nutrients to the surface layers and results in limited nutrient acquisition by photosynthesizing autotroph, decreasing primary production. Furthermore, stratification along the coastline, where a lot of fertilizer runoff and fossil fuel combustion adds excess nutrients, we're seeing an increase in harmful algal blooms that are depleting the areas of dissolved oxygen, expanding hypoxic and in some cases dead zones. When discussing climate change martyrs, few can compare to the significantly declining coral reefs. Studies have been conducted to analyze the increase in calcification of autotrophs that may be a response to artificial ocean alkalinization. Corallinales are red calcifying macroalgae that are an important feature of coastal ecosystems, as these species are the most prolific producers of calcium carbonate. In a study by Gore and Renfrew, the calcification rate of these autotrophs was analyzed under elevated total alkalinity, resulting in a calcification production increase of 60% over ambient conditions, with no significant changes to their primary production, respiration, or photophysiology. Corallinales are adept to large daily and seasonal fluctuations, thus their resilience may indicate a promising result from liming input.
So now that we've shown why global warming and ocean acidification are critical issues, we will present our proposal on how to target these. The three of us are members of Project Mirreflection with the Ye Tao Lab at the Roland Institute at Harvard. Mirreflection is an all-encompassing engineering framework using thin film-coated glass mirror arrays to feasibly and efficiently address the urgency of climate change.
Ocean liming is the dissolution of calcium oxide into calcium and bicarbonate ions. Here are the basic chemical equations we're working with. The molar ratios of the first equation tell us that liming allows the sequestration of close to 1.7 moles of carbon for every 1 mole of calcium ion added to the ocean. The change in free energy of formation for lime dissolution tells us it is highly spontaneous. And the second equation depicts the production of lime from calcium carbonate, which the common form is limestone. This process is endothermic at standard temperature and it releases CO2 emissions. However, when the solar thermal energy from our mirrors drives this reaction, it is much more energetically feasible for large-scale intervention. For our discrete calculations, we assumed a net flux of 11 petagrams of anthropogenic carbon input per year, which was the average for the period of 2009 to 2018. To neutralize this annual release of carbon via liming intervention, we estimate needing around 50 gigatons of calcium carbonate or 30 gigatons of quicklime. This would suggest the current global annual production of quicklime to be increased by a factor of 66.7. Given the amount of calcium ion found in the global surface mix layer, which we take to be a depth of 100 meters or less, we predict a 0.134% annual change in its concentration for each year of liming. We expect this perturbation in ocean calcium concentration to be small and localized, and it should be offset in the long term. Ocean liming is a geoengineering technology that has had limited research focus in the past. However, in assessing various methods for CO2 drawdown, we find that methods like direct air capture and mineral carbonation are not feasible or kinetically favorable. DAC is costly both energetically and financially, and mineral carbonation, though is cheaper and has relatively low energy requirements, is not as scalable due to limited resources of ultramafic rock. Conventional liming driven by fossil fuels is not energetically favorable, but there is an abundance of calcium carbonate sources. Additionally, carbon capture and storage in itself will only slow the rise of atmospheric CO2 rather than reducing it. We find that ocean liming is a viable strategy satisfying all of these factors when lime production is powered by concentrated solar energy and it is implemented alongside on-site CCS and reutilization. In this schematic, we see the simplest version of our liming strategy, where we mine limestone and power calcination with our mirrors. You can see that upon adding lime, a very rapid and selective acid-base reaction takes place, thus combating acidification from anthropogenic carbon dioxide uptake. We also see an immediate benefit to marine species such as coral, who rely on these ions for their structure. However, this is an open-loop system, which is not sustainable given the limited time at hand, because the ocean carbon content will increase over time while the atmospheric carbon dioxide levels stay constant and limestone reserves become limited. To solve this issue and close the carbon and calcium loops, we propose using waste mollusk shells, which are composed of calcium carbonate, as source material. This not only reduces the carbon dioxide burden of limestone extraction and processing, but also it enables a long-term cyclic strategy to produce a renewably sourced lime. It also boosts the economy through aquaculture, and it produces food for human consumption. It would additionally allow for the valorization of discarded resources, as in the mollusk shells, and it leverages higher primary productivity of oceans under carbon dioxide fertilization. Here we also show the storage of the concentrated carbon dioxide streams resulting from lime production. This happens through injection into materials such as basalt rock or deep saline aquifers, followed by the burial of these materials. However, just by burial, the emission flux sourced from fossil fuels do not equal the injection flux, and as a result, the atmospheric carbon dioxide levels stay constant. We propose another method being reutilization of these concentrated 100% carbon dioxide streams into via electrochemical catalytic processes into fuel that will power transportation. This method would contribute to the circular carbon economy. It also promotes a steady state flux all throughout these cycles, which means that all of the sources are balanced with the sinks. We do highlight the need to properly engineer the strategy and these solution loops for net positive ecological impacts upon execution. Thank you.